Give me a second. Hi, Jojo. Do I start right now? Or we should wait for another few minutes? So I'm a bit confused. Give me a second. Okay. Yeah, sorry, a little bit confused. So let's get started. Hello, everyone. I'm Wei from the University of Utah. My research makes parallel computing easier to handle so you can quickly boost your application performance. Today, I'm going to show you Taskflow, an open source C++ programming system that can help you quickly write parallel and heterogeneous programs. And you probably already know parallel computing is critical to advance your application performance. For example, a single-threaded machine learning program can take several hours or days to finish, but it can be reduced to only a few minutes or even a few seconds if we are able to run it in parallel. That's the power of parallel computing. By leveraging many core processing units, we are able to speed up the performance by several orders of magnitude. However, give me a second. However, writing a good parallel program is very challenging because you need to deal with many difficult technical details, such as standard concurrency control, task dependencies, scheduling, and data arrays, and many CPP developers have a hard time in getting them right, especially for those who do not have that much experience in parallel computing. So the Taskflow project is trying to address the following question. How can we make it easier for C++ developers to quickly write parallel and heterogeneous programs with high performance and simultaneous high productivity? By high performance, we mean the program runs fast and scales to many core processing units, including CPU and GPU. By high productivity, we reduce the time it takes to implement a program. Let's take a look at Hello World example in Taskflow. Suppose we want to do 4 things, A, B, C, D, each representing a function or a task. A has to run before B and C. D has to run after B and C. So this means when A finishes, B and C can run in parallel. When both B and C finish, D can start. This is how it looks in Taskflow. Only 15 lines of code to get a parallel task execution. This is all you need. You create a Taskflow object to manage a task dependency graph, and you create an executor that manages a set of worker threads to run Taskflow. Here we use the method in place to create 4 tasks in terms of C++ lambda and assign them to A, B, C, D using structure binding in C++ 17. To build out a dependency, you can use precede or succeed to relay dependency between 2 tasks. For example, in this case, we use precede to force A to run before B and C. And then we use succeed to force D to run after B and C. Finally, you can submit this Taskflow to the executor and it returns a future we can wait on it to finish. At this moment, I believe many of you can fully understand what this code is doing. The code explains itself through an expressive graph description model. Here is what I'm going to do in the rest of the talk. I'm going to show you how to express the parallelism in the right way by starting with the motivation behind Taskflow and applications we target. Then, I'll present how to use Taskflow to parallelize your application and give you a rough idea about our scheduling algorithm. Next, I will demonstrate some real use cases of Taskflow and show you how it can boost performance in large-scale parallel application. Finally, I will share with you some of our experience in using C++ to parallelize larger applications so we can enhance C++ to make it more amenable to heterogeneous parallelism. Let's start with number one. I'm going to show you how to express the parallelism in the right way by talking about the motivation behind Taskflow. Over the past few years, I've been working on parallelizing CAD software for integrated circuit system or VLSI system. CAD stands for computer-aided design. It is a software method to help people design integrated circuit or IC. Basically, you start from a high-level description of a hardware component and take it to the CAD software. And it generates a bunch of NetLists and synthesizes it into the physical layout. And you can use this physical layout to tape it out, to tape out the chip. So you can get a final chip that lives in your electronic devices. And this is a seriously complicated process. For example, the layout generation process requires different algorithms spanning across, for example, partitioning a graph of billions nodes, floor plan, placing millions of cells in a very small area, and routing trillions of wires to establish the signal connection and analyze the timing of all those billions components. And if you look at the computation, the resulting computational task graph in terms of encapsulated function code and task dependency can easily go up to millions of tasks with cycle, dynamic control flow, and irregular computational pattern that end up with several hours to finish. Because building a parallel CAD tool is very complex, and we want to find a programming system that can assist us with the implementation and deployment of parallel CAD algorithms so we can make the process run as fast as possible. To this end, we have invested a lot in existing parallel computing systems such as pthread, OpenMP, CPP thread, Intel TPP, and so on and so forth. Unfortunately, we found few of them can meet our purpose. The reason is as follows. We summarize two big problems of existing tool in this slide. First of all, our problem has very complex task dependency. For example, if you analyze the timing of a circuit, the algorithm requires you to compute the entire circuit network of billions of nodes and dependency. That is, the resulting task graph in terms of model function code and their dependency can go very irregular and up to billions. And the problem is, most existing tools are only good at, mostly are good at loop parallelism, but they are not very strong in expressing heterogeneous task graph at this larger scale, right? For example, OpenMP is very good at expressing parallel for loop-based parallelism, but it's not very efficient for irregular parallelism. The second, our problem defines very complex control flow. For example, optimization algorithm essentially make a lot of use of dynamic control flow to implement various combinatorial optimization algorithm or analytical method. And the problem is, most of the existing tools require you to describe a parallel workload in a direct acidic graph and they do not anticipate cycle or conditional dependency. So you are not able to describe a heterogeneous parallelism with control flow in end-to-end, because you need to partition your workload or algorithm across the control flow decision-making point and synchronize your parallelism at decision-making point. To better understand what this problem is, let's take a look at an example of an iterative optimization program. The program has 4 tasks and starts with the init task that initialize some data structure. And then it enters the optimization task to perform optimization. For example, solving a linear system using a GPU. Next, it moves on to the converge task to check if the optimization routine converge. If yes, it goes to output and stops. Or otherwise, it goes back to optimizer and do this optimization task again. And you can see the entire program has an iterative control flow over here. Doing this iterative control flow in a single-threaded environment totally makes sense. But it is very difficult to do it in a parallel environment. Think about it, you have multiple threads that are trying to make control flow decision. You definitely want to avoid frequent synchronization to happen or task race. After several years of research, we arrived at a key conclusion. We need a new C++ parallel programming system, and the takeaway here is, while designing parallel algorithm is always non-trivial, What makes parallel programming an enormous challenge is the infrastructure work of how to efficiently express dependent tasks along with an algorithmic control flow and schedule them across heterogeneous computing resources. That is the key motivation to support Taskflow. So next, I'm going to show you how we can use Taskflow to describe parallelism using a task graph in your application. For the next few slides, I'm going to show intensive coding example. Programming is quite subjective, so many of the arguments I make is based on my personal opinion. No offense, no criticism. It is just about C++ from a developer's perspective. In Taskflow, we define 5 different task types: static tasks, dynamic tasks, CUDA flow tasks, condition tasks, and module tasks. Static task is the most basic task building type in Taskflow. It takes a callable object and runs it. That's it. A dynamic task lets you spawn a task dependency graph during the execution of tasks, so you can do dynamic parallelism. A CUDA flow task lets you describe a GPU workload in a task graph and offloads it onto the GPU. A condition task lets you integrate control flow into the task graph so you can describe end-to-end parallelism. A module task lets you compose a large task flow graph using smaller task flows that are easier to optimize. In this Hello World example we've seen before, the 4 tasks A, B, C, D are static tasks. They simply take 4 lambdas and run them. So those are static tasks. The same Hello World example here, but written in OpenMP's tasking interface. We know OpenMP is a language extension to describe parallelism using compiler directives, essentially give hints to compiler and let compiler to decide a parallelism, generate a parallel code for you. It's a very popular parallel programming library. Almost all people start with to learn parallel computing. Using the same example, based on OpenMP, we have to use OpenMP task syntax to create 4 tasks, A, B, C, D. To build a dependency, we use a depend clause to specify the outgoing dependency and incoming dependency for each of the 4 tasks, A, B, C, D. For example, if you look at this task graph, A has 2 outgoing addresses. It has 2 dependencies, B and C. So we need 2 variables, A, B, and AC, to capture the constraint between A and B and the constraint between A and C. So this is how we specify the constraint by using OpenMP depend clause syntax. We specify the clause, the output dependency A to B and A to C for the task A. And we do the same thing for the other 3 tasks. The code is not very complicated, but it is static. You need to explicitly define everything such that the compiler will know how to generate those dependencies. Another big problem is that you are responsible for a proper order of writing these tasks, and that order has to be sequentially consistent with the sequential execution. Because when you compile this program with OpenMP disabled, everything falls back to sequential execution. So you gotta make sure the order you write those tasks is not breaking the dependency when they fall back to sequential execution. And this makes it very difficult to describe upfront parallelism. Same example again, but written in Intel Threading Building Block Library, or TBB for short. TBB is a general-purpose parallel computing library in C++. It has been used in industry for many years. The idea of TBB is very similar to Taskflow in a sense it describes dependency graph using a flow graph. You create a flow graph and then use this amongst the class template, continue node, to create 4 tasks, A, B, C, D. And then you use another big template continue message class to describe dependency between A, B, C, D. And finally, once you finish a description of that task, you use this C star function called the relay dependency. For example, make age A, B. That means I want to create a dependency between task A and B. When you finish a description, you have to identify the source task manually. In this case, the source task is A, and that is the task you have to start with. And you submit the source task into the scheduler. And finally, the TBB will launch the scheduling to execute your task graph. According to our research, TPP has really excellent performance, especially when you are running on Intel architecture. And it turns out many API defined by TPP is overly complex, even though they are very powerful. And I would say the main drawback is mostly on the ease of use standpoint in terms of simplicity and expressivity when programming a parallel program. What I presented to you was my personal interpretation, and it can be biased. So I did a survey. I asked about 100 students. They are learning parallel computing, learning parallel programming in C++. And I asked them this question: how would you like to express a larger task dependency graph, approximately like 10 tasks or 15 dependency? It's very small. And vote for the following 5 different libraries: Taskflow, OpenMP, TPP, Cocos, and StudThread. And what I'm trying to discover is how C++ learner think about this parallel computing library, especially for those who are just getting started to learn parallel computing. This is how it looks. About 74% will prefer to use Taskflow if the application workload depends on a lot of tasks and require many dependency between tasks. More importantly, the number one concern they have is my application is already very complex, and I believe this is a very common concern for many developers. My application is already very complex. It's very important the parallel programming library does not become another burden for me to parallelize my application. The previous examples were all static tasking. You describe the task to spawn at the first level of the graph. And we can also do dynamic tasking. You can spawn a task dependency graph from the execution of a task using a dedicated interface subflow. In order to create a subflow, you place a lambda with an argument on subflow, and you describe another task dependency graph inside that subflow. For example, here we create a task dependency graph for the execution of task B. And the subflow will spawn another 3 tasks, B1, B2, and B3, where B3 runs after B1 and B2. So in terms of coding, inside the subflow, you create 3 static tasks that represent B1, B2, and B3, and then use the same method preset to force B1 to run before B3, and use the preset again to force B2 to run before B3. So when the scheduler finishes at the execution of A, it starts running B, and then it spawns another task dependency graph inside that subflow, and runs B1 and B2, and then B3. Eventually, the subflow joins its parent task B, and then we move on to task D. This subflow can be nested. You can create a subflow from another subflow and so on. And this is an example of a task graph that tries to find the 7 Fibonacci number using subflow. Fibonacci number is a series of numbers where each number is the sum of the previous 2 numbers, and it can be done with a recursive parallelism. For example, if you can see from this diagram, we start from a task doing a Fibonacci number at 7, and it spawns 2 subflow on 5 and 6. In the subflow 5, it spawns another 2 subflow 3 and 4. And so on and so forth, to calculate a Fibonacci number recursively. So we have finished dynamic tasking. The next task type is CUDA flow. You can offload a task to GPU, and we manage heterogeneous CPU-GPU tasking through a closure-based interface CUDA flow. A CUDA flow is a task associated with a CUDA graph, which is a new feature in NVIDIA since CUDA 10 and enhanced in CUDA 11. A CUDA flow is very similar to subflow. It takes an argument of CUDA flow, and that will be created during the execution of that CUDA flow task. Within this CUDA flow, you describe multiple GPU work, multiple GPU operations such as data transfer and launching kernel in a task dependency graph instead of aggregated operation using string or buffer. In this case, we have 2 copy tasks trying to move the data X and Y from CPU to GPU, and a kernel task that offloads a written kernel to GPU, and another 2 copy tasks to get a result back from GPU to CPU. And so you can see the kernel has to run after the copy test from host to GPU. And it has to run before we copy the data back from GPU to CPU or the host. By leveraging the power of CUDA graph, we launch the entire GPU task graph in a single kernel call instead of multiple one. In this case, if you do not use this graph description, you might encounter 5 GPU operation. So we can, in this case, we can largely reduce the overhead of kernel code. And when you finish the description of the GPU task graph, you can pipeline the entire CUDA flow with other CPU tasks or other CUDA flow. So we can overlap all these different tasks in the task graph. And this is very important because CPU, GPU programming always involves some sort of data transformation at very expensive cost. Without a suitable task graph interface, it's very difficult to express this overlap. And why do we do this closure-based design? Well, first, our closure enables stateful interface. You can capture data in reference to marshal data exchange between CPU and GPU tasks. This is a key because for graph parallelism, when everything is formulated as a task dependency graph, you gotta make sure the computation result of CPU tasks are visible to GPU tasks, or vice versa. For example, CPU tasks compute the data size, allocate the memory, and then the GPU tasks know how to set up the kernel parameter based on the result computed from the CPU tasks. Second, the interface is advantageous in hiding implementation detail, and it provides a lightweight abstraction over GPU implementation. If you look at the CUDA flow interface we have, you don't really need to deal with too many CUDA specific code instead of describing kernel and all this operation in a task graph. We have just finished the heterogeneous tasking interface in Taskflow. The next I'm going to talk about is condition tasks. Conditional tasking is a very powerful interface to enable dynamic control flow. And we believe this is one of the key features that stands out Taskflow from other libraries. You can create a condition task that returns a value indicating the next immediate successor to run. In this example of iterative optimization workload we have seen before, I have a task graph of 4 tasks: init, optimizer, converge, and output. Init task initialize some data structure we need for optimization. Optimizer task launches the optimization routine such as solving a linear system, for example. Converge task checks if the optimization converge, and it phones a cycle back to the optimizer if we haven't reached convergence, or moves onto the output task and stop. And you can see the converge task here is a condition task, and it precedes 2 tasks, optimizer and output. With this order, when it returns 0, it goes to optimizer again. It informs the scheduler to re-execute the optimizer task again. When it returns 1, it informs the scheduler to proceed the execution to output. There are ultimately 4 tasks ever created in this iterative optimization workload. You describe iterative workload in a whole graph entity. There is no need to partition your graph and synchronize it at each iteration or wrap your task graph in an inner loop or for loop. And this condition task can indeed handle more complicated scenarios such as nested or non-deterministic control flow. In this example, I have a task graph of 5 nested cycles. Each green task over here is a condition task. It flips a binary coin by calling a random function, scale it to 1 and scale it to 0 and 1. So this is a binary coin flipping to decide the next path, either move on or go back. If it returns 0, it moves to the next task. When it returns 1, it goes back to the first condition task and reflip the binary coin again. You can see there are 5 such tasks to flip a binary coin. So the average number of condition tasks you may run through before reaching the task end is 32, because we got a probability of 1/2 at each condition task for us to move up. Similar to the previous example, ultimately, we only use 5 condition tasks to describe this nested and non-deterministic task execution, even though we may end up with averagely 32 execution. The scheduler will reuse all these 5 condition tasks. All right, so I got a question. Do you think Taskflow can be suitable for streaming scenarios and where each task generates a large output over time to be processed by its successor? And I would say it depends on how you want to process your stream. You can always describe the computation in a task graph that takes the input of the stream. And you can pipeline those task graph across different stages of your stream. All right. So let's move on to the next slide. How do we do this condition in existing framework? And we know many of the existing framework are based on directed acidic graph, and they do not allow cycle. And I'm not talking about a cycle you have in like pipeline, but a generic interface for you to describe control flow in a parallel task graph. So this is also relates to what I just response. You can always use condition task to describe a task flow. So to loop a task flow graph in a stream. And the most common solution is to expand the task graph if you use existing framework that does not support condition tasks, to expand their task graph across fixed length iterations. For example, if you happen to know a loop condition or a streaming loop that is going to take 5 iterations, and you can unroll the task graph, right? You can duplicate a task graph by 5 times and concatenate them together. Of course, the result of that is increased graph size and memory consumption. But what about a loop of unknown iteration like the streaming application or non-deterministic conditions? You may spawn dynamic tasks executing if statement on the fly to decide the next execution path, but that often gives you rather complicated implementation recursively, and that is not a very good choice. In fact, according to our research, for generic condition, existing framework typically has the problem of exponential growth of coding complexity. So I have another question over here. Can Taskflow be used to handle file descriptor or timer events so it can replace a boost SEO? The answer to this is no. I would say what we are trying to do is to complement many of the existing, whether it's an event-driven library or parallel programming library, because a Taskflow essentially is a multi-threading library that you describe application in terms of Taskflow graph, and then we do multi-threaded. We spawn multiple threads to schedule your execution. But Boost SEO is particularly good for IO-intensive application. And I would say Taskflow is good for compute-intensive application. So both libraries can complement to each other. For example, you can use the Boost SEO when you get an event, when you got some input from the data source, and you can spawn a task dependency graph to process that event based on whatever data you receive. All right. So let's take a look at the final tasking type, and that is composable tasks, composable tasking. Taskflow's task interface is composable, and this is a key element to improve programming productivity using composition. You can create multiple task flow, each representing a portion of your parallel decomposition strategy that is easier to optimize at smaller scale. Then you can assemble this task flow to form a large task flow that composes correctly and efficiently. In this example, we have a 2 task flow, F1 and F2. F1 has 2 tasks, F1A and F1B. F2 has 4 tasks, F2A, F2B, and F2C, and a module task composed of task flow F1. You can do this composition in just one line of code using the method compose of. So in this case, I have created 2 task flow, F1, F2. In F1, I place the 2 static tasks that represent F1A and F1B, and there are no dependency between. In task flow F2, I first create 3 static tasks that represent F2A, F2B, and F2C, and then I relay the dependency. Inside Taskflow F2, I use this compose of method to create a module task that eventually represent the execution of a Taskflow F1. So when you finish the description, scheduler will start with F2A and F2B. When both F2A and F2B finish, it invokes this module task to spawn another task flow graph and run F1A, run F1B, and finally, when both finishes, we enter F2C. So this is how composable tasking works. We can partition a large task flow into several smaller task flows that are easier to compose and optimize individually. The biggest advantage of Taskflow is everything is unified. You use the method in place to create a task. It can be either a static task, dynamic task, condition task, composition, or CUDA flow. And you use the single method preset to relay the dependency between tasks. And you can create a really, really complex graph that combines all the 5 different task types and integrate control flow into your task flow so everything runs end-to-end. When you finish the description, our schedule will perform end-to-end performance optimization on runtime, energy efficiency, and throughput. This is another example of using Taskflow to describe a k-mean clustering using CPU and GPU tasks. And k-mean is a clustering algorithm that tries to find the best k-centroid among a set of points. K-means is iterative. You have a CPU and GPU task running iteratively to compute a k-centroid. Here we use a single task flow to represent the entire k-means workload. We have one CUDA flow to perform host-to-device data transfer, another CUDA flow to perform kernel to offload the computation to the GPU that finds the best k-centroid of the current iteration. And then we have, because it's an iterative process, so we use the condition task to model the iteration. If it's not converged, we loops back to the CUDA flow again. When we converge, then we have another CUDA flow to perform device to host data transfer to copy the result back from GPU to CPU. We have just learned all the core programming models of Taskflow to describe a parallel program using a task dependency graph. Being a C++ developer, not only do we care about the expressivity of a library, we also need performance, and that needs efficient scheduling algorithm. So I'm going to show you our scheduling algorithm and how we can submit a written task flow with control flow into execution engine executor. An executor is where you can submit a task flow to execute tasks defined in that graph. An executor manages a set of worker threads to run task flows. All execution methods in Taskflow executor are non-blocking and fail-safe. So you can do pretty much whatever submission you want. Let's take a look at this example. Suppose we have a 3 task flow graph, task flow 1, task flow 2, and task flow 3. And then we have an executor. We define several methods to run task flow. For example, you can use the method run to run a task flow by one time. Or use the method run n to run a task flow by n times. In this case, I run task flow 2 by 1,000 times. Or you can specify the stopping predicate. And when it becomes true, we will stop by using run until method. For example, in this case, I will keep running task flow 3 until the variable I becomes larger than 5. So this will run task flow 3 by 5 times. In addition to running a task flow, you can also launch a task synchronously using the STL*async function code. And this makes it very handy if you want to just create a task on the fly or simply use our executor as a thread pool. And the scheduler will autonomously ask you all the tasks and decide which worker to run which task. I got another question over here. A module task seems similar to dynamic task, but defines before execution instead of during the execution. Is this a reasonable observation? Is there a benefit in using module tasks instead of dynamic tasks? And yes, Essentially, module task is very similar to dynamic task, but what we separate the definition is because a lot of time you can partition a very large workload into several pieces, and you can ask your teammate to give you a task flow graph. Because with the task flow, with the entire task flow, you can do much more powerful thing. For example, you can profile a task flow, but you are not able to profile a subflow until you run a task flow. So this makes the workload distribution more efficient. And we will talk about this later when we move on to the profiler. So our scheduling element has two levels, task level and worker level. At the task level, the goal is to decide how tasks are in queue into the wait list under control flow because we have condition tasks. At the worker level, we decide how tasks are executed by which worker. So in order to schedule tasks under control flow, we define two dependency types, strong dependency and weak dependency. A weak dependency is the dependency coming out of a condition task. Others are strong dependencies. For example, in this optimization workload, iterative optimization workload we've seen before, the two dependencies coming out of the converged tasks are weak dependencies. So the task level scheduling flow is as follows. When you submit a task graph, it starts with a task of no dependency. Those are the source tasks you have to start with, including both strong and weak dependencies. In this case, we will start from the init task because there's no dependency, right? And when a scheduler asks you a task from the queue, it branches the execution depending on the task type. If it is a condition task, it invokes the callable. It invokes a condition task, gets the return value from a condition task, and jumps to the pointed successor. In queue, that successor at the index return from condition task. If it is not a condition task, it simply invokes the callable. Decrements the strong dependency of each successor by 1. And then in queue, those successors whenever dependency are met, when the dependency becomes 0. So you can infer that without these condition tasks, if you remove the part of conditional tasking, the scheduling algorithm falls back to the normal directed acyclic graph execution. And this condition task is quite powerful for you to describe control flow in a task graph with end-to-end parallelism, but it's also very easy to make mistakes. For now, it's users' responsibility to ensure a task flow is properly conditioned based on our execution logic. That is, you should avoid task race under task level scheduling policy. So let's take a look at two common pitfalls when using condition tasks. The first example, we have a condition task A and it precedes 3 tasks. Task A itself, task B, and task C. The problem with this graph is it won't get scheduled. The scheduler will not schedule this task graph because there are no tasks for us to start with. Remember, we always need to start with the task of no dependency, including both strong and weak dependency, and there are no such tasks for us to start with. So the fix number 1 is to add a source task, S, and have it precede the task A. So we can start with S and then move on to task A. Depending on the condition, we will loop again to the task A or move on to task B or task C. The second pitfall here is, here we have 4 tasks. E goes to D, and the condition task C goes to D and goes to F. In this case, you may run into task race because when both E and C finish, because they have no dependency, they will start in the beginning at the same time. When they both finish, when E finish, it includes the task D. At the same time, if task C returns 0, if the task C returns 0, the scheduler will include task D. Then we may race on task D. To get this fixed, we have to add an auxiliary node between task D and task C. And this, in fact, is to tell the scheduler that the task D is conditioned by 2 situations. Both E finishes and C returns 0. If you look at a sequential control flow, and it totally makes sense because we are not able to run test D until both conditions become true. At the worker level, we use work stating to run tests, and this is a masterpiece of work, and we have spent a lot of effort over the past few years, and unfortunately, I won't be able to cover all the detail, but I will try to just give you a very high-level impression about how it works. So what is work stating? In a nutshell, it's a dynamic scheduling algorithm. I finish my job first, and then I steal job from you. So we can improve performance using dynamic load balancing. When a worker thread drains out its task queue, it tries to get some more tasks from the other worker. This is essentially the key idea behind work stating. So we can do this load balancing in a decentralized fashion. And there is an excellent talk about work stating at CPPCon 2015 by Pablo Halpin. You are definitely encouraged to watch the video for more detail. When you finish the execution of a Taskflow program, you can use our web-based interface, TF-Prof, Taskflow Profiler, to profile your Taskflow execution. TF-Prof will visualize the execution timeline of your program and rank the top critical tasks in a bar chart. And our profile is written in JavaScript and D3, so you can easily run it in your favorite browser. And this is the profiler I mentioned before. With Taskflow, you are able to profile a Taskflow using a profiler. But if you want to, and this is why we need this module task interface, because when you describe your workload, when you partition your workload into different modules, you can profile each module individually. They are easier for you to optimize. So definitely click on the link and check it out. And we do have a spatial algorithm written in JavaScript. We try to visualize a very large Taskflow graph. So we do some clustering algorithm. We have understood the scheduling algorithm in Taskflow. Next, I'm going to present to you some of the results we have obtained by applying Taskflow to real application. And this performance data is another big thing we really care about. The first application is a VLSI placement workload we have applied Taskflow to solve. VLSI placement is a very important step in the circuit design flow. Essentially, it optimizes the cell location on the chip. A cell is a gate like OR gate, NAND gate, NOT gate, and so on and so forth. In modern design, you can imagine there are millions of cells in the placement optimization. They can take several hours to finish. And the challenge of the placement optimization is it makes essential use of control flow because it's an optimization. To describe iteration, we use condition tests. To speed it up, we implemented a GPU accelerated algorithm in DreamPlace, and that is a very famous placement algorithm developed by a group in UT Austin. And here is a partial task flow graph of 4 CUDA flow, 1 condition cycle, and 12 static tasks to describe this tiny fraction, only a tiny fraction of the entire graph. And keep in mind the entire placement computational graph is much larger than this. And we compare the performance of Taskflow against TPP and StarPU, which are 2 popular task programming libraries. And we measure the performance in terms of runtime, memory, and energy efficiency in these 3 figures. Blue line is Taskflow, red line is TPP, light blue is StarPU. On the top left figure, the runtime plot, you can see Taskflow is faster and the difference is faster than the other libraries. And the difference starts to increase when the problem size becomes larger. All the 3 libraries, all the 3 algorithms saturate at about 16 CPU core. But before that, we found Taskflow is always faster. Because this placement optimization workload is iterative, so we use condition tasks to model the control flow. But for the other 2 libraries, they do not allow cycle, so we flatten their task graph across placement iteration. And of course, the result of that is the increased memory. So you can see as we increase the problem size, the memory keep constant. But for the other library, they suffer from increasing memory growth. Of course, this increase in memory size and also contribute to a lot of other factors. For example, energy efficiency. In this power data, we can see in order to finish this workload, Taskflow is more power efficient than the other. And the second example is a real application on machine learning. And we try to compute the inference of a very large deep neural network. Has 1920 layers of each of 65536 neuron. And this entire network can take up to 50 gigabyte memory. And that is also the graph challenge problem given by the HPEC community, high performance community. So the figure here is a partial task flow graph of 4 CUDA flow, 6 condition tasks. 6 static tasks and 8 condition tasks to describe the cycle for this iterative machine learning workload. Each CUDA flow contains thousands of GPU tasks. So you can imagine that if you launch this GPU operation, thousands of GPU operation one by one, the overhead is going to kill the entire performance. Because the network is very large, so the advantage of task graph parallelism starts to come out. The slide shows the performance data. We compare again Taskflow with TPP and StarPU because they both support graph parallelism. And this machine learning workload is iterative. So again, we use condition tasks of Taskflow to model the control flow. And because TPP and StarPU do not support control flow or iterative cycle in their graph, we unroll their test graph across iteration. Figure in the middle shows the runtime and memory at different CPU and GPU number. Again, the blue line is Taskflow, red line is TPP, light blue is StarPU. In general, you can see Taskflow is much faster than TPP and StarPU. It's about 2x faster when the graph becomes larger and larger. And memory is also about 1.6x less. We attribute this result to the use of our condition task. By using conditional tasking, we are able to describe the entire workload in a single task graph with end-to-end parallelism. There is no need to explicitly synchronize or partition your parallelism across the decision-making point. So I would like to summarize this result with a key takeaway. Parallel programming infrastructure is just as important as the parallel solution itself. Different programming models are going to give you different implementation. Keep in mind, the parallel code or algorithm itself may run very fast, yet the parallel computing infrastructure you use to support that algorithm, including all the surrounding data structure you need, may dominate the entire performance. This is especially important when you consider heterogeneous workload because control flow decision making frequently happen at the boundary between CPU and GPU tasks. If you do not have a dedicated interface for expressing CPU-GPU dependent tasks, along with algorithmic control flow, the overhead to partition or synchronize your heterogeneous parallelism is going to kill the entire performance or outweigh its performance benefit. So I got a question here. Does the current scheduler and scheduling algorithm use const_expr to move some logic to compile time? This is very interesting. No, we do not use this compile time optimization, but I'm definitely very interested to explore this, especially you are able to describe the task graph, right? When the compiler will be able to see at least certain structure of the task graph, so we can do some optimization like fusing two tasks together. And this is something maybe we can talk about offline. All right. So thanks for the very good point and suggestion. So far, we have seen the performance of Taskflow in real application. We talk about large-scale machine learning application and a VLSI optimization workload. Now, I'm going to share with you some of the experience we have learned from using C++ to handle large-scale parallel application. And hopefully, our experience can contribute to making C++ more amenable to heterogeneous parallelism. The first point I would like to make is parallel computing is never standalone. It beats nothing if it doesn't apply. No one will buy a parallel computing library without application. So we must bring parallelism to practice and apply it to applications. Given a tremendous amount of application, I don't believe a single model or API can express all the different parallelism. We need multiple C++ and expert in parallel computing and application from either academia or industry, because each of them has expertise in certain application and domains. For example, we cannot rely on a single powerful language or compiler. Right? Over the past, we've seen many compilers trying to unify all the different parallelism. And I just don't think that is going to be possible, because once you rely everything on compiler or programmer, the scalability will become an issue, right? And here is how I think about the current status of CPP parallelism and this existing progress. For me, C++ parallelism is still very primitive, even though it's very low level and powerful. For example, Stu thread is very powerful, but it is very low level, right? And you can also use a little bit higher level API like a Stu async to describe, to launch a task asynchronously, get a feature that will eventually hold the result to that async function. But there is no way for you to describe dependency between these async tasks. And that turns out to be more important, right? If your application has no task dependency or data dependency, then it's perfect. You can easily launch multiple threads to saturate the memory of your and to get the best performance of your application. But that's not the case. There are no easy ways to describe control flow in C++ parallelism. For example, if you look at C++ 17 parallel STL, the only possible parallel infrastructure you may use is box synchronous parallelism. You run something in sequential, and once you reach some point, you can do something in parallel. You fork multiple threads to run parallel algorithm. And then you join the synchron and synchronize those threads again, moving on to the next sequential block, and do this over and over. Also, there are no standard ways to offload tasks to accelerate such a GPU. To sum up, we have presented Taskflow as a general-purpose parallel tasking tool. Introduces a simple, efficient, and transparent tasking model for C++ developer to quickly write parallel and heterogeneous program using minimal programming effort. We also talk about some general ideas about our executor and scheduling algorithm, and we demonstrate its promising performance in large-scale machine learning and VLSI CAD application. There are many excellent efforts from the C++ community on the parallelism. Like I say, our Taskflow is not to replace anyone, but we are trying to complement the current state of the art and address their limitation on the task graph parallelism. So we can use Taskflow together with all the other library. And Taskflow is header file only, so integration shouldn't be any issue. We totally rely, the only thing we rely is the standard template libraries. There are no third-party library dependencies. And we are very open to collaboration when we believe collaborative effort is the only way to make C++ more advanced on the front of parallel computing. And right now we are using CUDA for our GPU testing, but we definitely want to integrate, for example, OpenCL, SQL, or Intel's DPC++. And we want to provide more high-level algorithms and on top of our task graph. If you ever use Taskflow, please let us know, and we want to learn from you and broaden our real use cases. I would like to take this chance to say thank you to all the users. There are quite a few people using Taskflow right now. I'm very grateful for the tremendously useful feedback from all of you. And again, I'm very open to collaboration where you are interested in using Taskflow, understanding more technical details, or chatting with me so we can talk about more C++ and heterogeneous parallelism. Here's my email. Feel free to ask me any question. You can also find more detail about Taskflow at this GitHub link. With that, I'm going to cut here, and thank you very much for your participation. So I got a question over here. Is there any way to serialize Taskflow graph into a custom file format? As this is relying on lambda type, I guess everything needs to be defined at compile time. This is an excellent question indeed. Some of our users also ask us this question. because if you want to do, for example, like a distributed computing, then being able to serialize a test flow will be a big plus. But like you say, right now everything is relying on lambda, so we haven't come up with a good way to serialize a test flow graph. But I'm very open to any suggestion. So the short answer to your question is no. We don't know how to serialize a test flow graph because, like you said, everything is based on this lambda. You can arbitrarily capture the data, and we have no idea what you are going to do inside a lambda, unless we try to modify the compiler. The next question is, when scheduling some very trivial tasks, how much overhead is there in Taskflow? How big should tasks be? Make it work scheduling them with Taskflow, or make it work scheduling with Taskflow? This is another very excellent question, because when people come out with this task graph algorithm to describe application in a task dependency graph, the very important point they always come into their mind is the overhead. Right now, creating a task takes about 70 nanoseconds. It's amortized cost because ultimately under the library we have a task pool, we have an object pool to recycle those tasks. But yes, creating a task does have some overhead because eventually we use stu function to store those callable objects. And the overhead is about 10 nanosecond to 70 nanosecond. So if your workload, if your task is within the scale of 10 microsecond to 100 microsecond or even a few milliseconds, then task graph algorithm is my fit. Is a good fit. And this is true for all the task programming library. And we always need to understand the cost of creating a task, scheduling a task in order to decide the best granularity of your application. Because you need to partition your workload into multiple tasks. Yes? Any other question? Yes, there is no zero cost abstraction. Yeah, question in stream. Oh, let me see. So I have a question. Sorry, I did not notice the private chat has also some question. So let me open the private chat. Does Taskflow has an internal scheduler above the system scheduler? Internal scheduler above the system scheduler? What kind of system do you refer to? And then let me try to answer this question. We do have our own scheduler, and it's at our library level. And I'm not quite sure what do you mean by the system scheduler. But we build our own scheduler, and by using work stealing. Yes. Oh yes, we do have a scheduler at library level internal. So the next question I have is, how does Taskflow manage transfer of data from GPU and CPU and vice versa? This is an excellent question because when you do CPU-GPU computing, data transfer is usually a non-negligible cost. We do this data transfer by two ways. First, if you use library code like unified memory addressing, like CUDA memory malloc manage. So you can get a chunk of memory that is shared between CPU and GPU. In this case, the memory management is very, very easy because we rely on CUDA runtime to do the memory transfer for us. And this is one way we highly recommend. And that's the first manner for doing this data transfer. And the second way we do the data transfer is to expose this copy data between CPU and GPU to the API defined in CUDA flow. So you can do explicit data transfer, user can have the full opportunity and full power to do the data transfer migration between CPU and GPU, or even between GPU, if you need to handcraft the performance in very detail. How does Taskflow compare to C++, A, and P? I would say there are many tasking libraries, and it's impossible to compare Taskflow against all of them. And I would say the biggest advantage of using Taskflow rather than existing similar library is the following. First, our interface, we believe our interface is very clean and expressive, because our team built Taskflow from application. We have been doing application for many years, and indeed, Taskflow before version 1, Taskflow was internal to one of our commercial products. And later on, we found it very interesting, so we isolated this component to make it a more open source project that can benefit generic C++ developer. So the interface is cleaner and more expressive, I believe. Second, we allow you to integrate control flow into a single graph entity, so you can describe end-to-end parallelism. And like I said, this is one thing I think that stands out Taskflow from the other existing library, because we have this conditional tasking. You can pretty much describe all the different control flow and integrate the control flow decision-making point into the task graph by building the dependencies. So you can achieve end-to-end parallelism. All right, I would say that's the two main advantage. But of course, different library have their own application domain. So it's really hard to say one is better than other, or one is always better than other across all applications. That's not impossible. So next question, can a subflow graph return to an IDL and pass them to Taskflow to be parsed? To be honest, I don't know very clearly, but I think somehow this question is related to how we can serialize the Taskflow graph. And the answer to this, I would say the answer to this is no, because we rely on everything we rely. So we rely on two things. First, we describe everything in Lambda, and we do not do memory abstraction or simplify this simplify this kernel programming, because those are application dependent. And if you do not do this memory abstraction, then it's very difficult to have another like data abstraction serialization interface that you can describe a graph of line using like IDL or serialize the graph to whatever format. So the next question I have is, I heard good things about Silk Scheduler. Do you know that? Yes, I know Silk Scheduler. Silk is one of the frontier that do work stealing. But like I say, the scheduling, well, we do have a specialized scheduler that has to work on. Initially, we used some idea very similar to the Silk scheduler, but later on we found the default scheduler designed by Silk is not workable for our case, because we have control flow. So think about our dependency graph has cycles. So we need a very specialized work stealing scheduler to handle this case. Second, Silk relies on fork join model. It does not tackle task dependency graph. There are some other variants on top of Silk scheduler that can handle task dependency graph, but ultimately it still rely on fork and join. So just once you reach some point, you fork another execution point using either code routine or forking another flag to run those tasks. Then in underlying, you can use the work stealing to do load balancing. So the branch factor is always 2. That's based on my understanding about Silk. So the execution, if you visualize the execution or scheduling of a Silk, it is indeed a binary tree. Technically speaking, it's not a dependency graph, so they're still different. Any other questions?